Okay, so how's everybody doing today? Tired. How did it go with the assignment? Annoying? Okay, it's time to stop talking now. How did it go with the assignment? Well, assignment one, the one that you hopefully submitted by now.
Almost forgot part two.
Almost forgot part two. I actually took a look at the zip file that of all the assignments submitted. It seems there's a good number of people who forgot part two. So part two is submitting your testing. You know, if you did that, well, don't worry, the TAs will tell you. The assignments are being marked as we speak. One thing that I don't want to cause a lot of stress for you is the way CU Learn seems to be configured right now. As soon as a TA enters the mark and comments on your assignment, you'll receive an email and or the mark will appear on CU Learn. That's fine, except the TAs don't simultaneously mark 300 assignments, so some of you will receive your marks while others are still waiting. Don't panic because you didn't receive your mark, but your friends have. Yeah?
Do you ever want us to do the test stuff, like exactly how you did it on the bottom of the page, or our own variations of tests, or
Something similar to what I did on the bottom of the page. You can do it a little.
we do exactly like input the same values you did and then go through it, or?
Yeah, that's typically fine.
Okay.
I mean, it's the testing I do is not exactly thorough. It's actually more to explain the questions in some cases, because it's hard to write unambiguous questions, but it's usually easy to know what's meant when you see the example output. Okay. Other issues, questions? Now's your chance. So I'm surprised to see so many of you. A couple of days ago, or a day ago, I posted a recipe for viewing the YouTube videos at twice the speed. So there were about half the number of people in class this morning in the other section. So don't do that. It's not a good idea. Come to class. It's easier, and when something is confusing, at least you can interrupt me and ask me about it. And that's the reason we have this class. So you should never feel uncomfortable putting up your hand and asking a question. Okay. So what have we learned so far in this course? Well, we've learned about numbers. We have learned about strings. We've learned about lists, or arrays, as I like to call them. And we've also learned, this is not sounding good. Does that sound as bad to you as it does to me? Yeah. Would you rather that I just turned it off? Okay. So that'll require that you guys be relatively quiet. So don't talk to your neighbors in class. So we've learned a few things. In addition to learning about lists or arrays, we learned these methods for iterating over the elements in a list or an array, and for filtering a list to get another list that contains a subset of elements that satisfy certain criteria. And we've learned how to derive one list from another. So different kinds of iteration and things, but all of this to do with lists. So today I actually want to, in some sense, finish the course for you, because after today you will learn all of the basic constructs for programming in a procedural language, and more formally, you will know enough that you can compute any function that is computable. So after today, you'll know enough of Python to be able to compute anything that can be computed by a computer. So great, we can all quit after this, after the fourth class. Not exactly. Think back in terms of, yeah, I can show you what a piano is and where the various parts are, and I can show you all the keys on the piano, even tell you their names, the names of the notes that they play. But that doesn't make you a great piano player. So there's still lots of work to do to get you guys good at programming. But just know that after today, you know enough to do just about anything that can be done with a computer. So there will still be more to learn for the remaining 11 weeks of the course. Okay, so I guess the first thing I want to talk about today are conditional statements, or as you're more likely to call them, if statements. So let's try and write a really simple function that needs a conditional statement. So anybody heard this term absolute value before? Yeah. So what's the absolute value of a number x? It's somehow the x where you forget about the sign, or maybe you could, well, there's a few ways to define it, but it's basically x if x is bigger than or equal to 0, or it's minus x if x is less than 0. Yeah.
Is writing DEF or
Oh.
overdefined the same thing?
No, that's me programming badly. There we go. No, define doesn't mean anything in Python. So we want to write this function absolute value of x, and I've just told you its definition. There's two cases. If x is bigger than or equal to 0, the absolute value of x is x, and otherwise it's minus x. So that in either case, the absolute value is a positive number. So we might as well just write it. And if x is less than 0, then the absolute value of x is minus x. So we'll return minus x. And if x is not less than 0, that means it's bigger than or equal to 0. So otherwise, we'll return x. Okay. So I've just shown you an if statement. The if statement takes an argument called a condition that is a boolean value. It interprets as a boolean value. So in this case, if the condition x is less than 0, if that's true, then it executes this block of code that occurs right after the if statement. And if it's false, this if statement has an else clause. It executes this block of code that occurs after this else clause. So let's test that. And so we want absolute value of 32 is 32. Absolute value of minus 32 is also 32. So you see that when we give it the input minus 32, it checks if the input is less than 0. It is, so it returns minus 32, which is just 32. And when we give it the input 32, the 32 is not less than 0, so it executes this second part. Anybody see any shortcuts for this function? Anything we could do to make it a bit simpler? Yeah.
Can you just use the ABS function?
Yeah, so you can use the math library function ABS. That's not what I had in mind, though.
Okay.
Yep.
Can you just square root it?
Yeah, you can write a math formula that does ABS also, but so you take the square root of x squared. That'll give you the absolute value also, but it's not quite what I had in mind, and it's also much more expensive or much slower to do it that way. Yeah.
In the
if statement, instead of return negative x is equal to negative x, then remove the else statement and just have return x outside of there?
Okay. So the suggestion is that maybe this else isn't needed here. In particular, maybe this works just as well. So let's think about that for a second. So we never looked too carefully at control flow and exactly what happens with the return statement. So I think all the examples we did have a return statement usually at the end of the function, so the function returns and ends. But a return statement actually does something stronger than that. So whenever you put a return statement into a function and it gets executed, that's it. That's the end of the function. This value is returned and nothing executes again after that. So here we say if x is less than 0, return minus x, then that's it. The function is over in that case if we return minus x. This next line won't be executed. On the other hand, if x is bigger than 0, this line doesn't get executed, and the next line does get executed. So somehow the else was unnecessary there. Let's just test that that's correct. So absolute value of 32. The first return does not get executed, the second one does. And absolute value of minus 32. The first return gets executed and then the second one doesn't. Okay. So a return statement inside a function like this, inside a function definition, that's it. If you hit that statement, the function finishes at that point. It doesn't matter if the return statement is inside a loop or if it's inside an if or if it's inside something else. Basically, the first time you hit a return statement, the function is done, and control goes back outside the function. In this case, it goes back to the Python environment. Some people prefer not to have lots of return statements inside a function because it sometimes can get confusing. So the reasoning is that it's easier to understand a function if it always runs from beginning to end and then returns on the last line of the function. So is there a way to get to write this function that way? Yeah.
You replace the return negative x with x times equals negative 1 or x times negative 1.
Or x equals negative x. Yeah. So so if we want that nice form of a function with only one return statement right there on the last line, then instead of returning negative x, we can just reset x, negate it, and then it returns that value, this new value of x. And we can check that as well.
Would that have an impact on our QRS
No, the TAs are not so fussy about that. So not everyone believes that every function should have exactly one return statement. I'm not sure I believe it myself. It's more, it is a nice way to write functions, but if you find that the whole logic of the function is getting really complicated and the only reason is because you're trying really hard not to use return statements inside, at some point it just becomes easier to understand it and understand what's going on if you just use the return statements where they're needed. So don't put all kinds of convoluted logic just to get you to the end of the function so you can return there when all you need to do is put a return statement in the inside. Okay, so there's a fairly short definition for the absolute value function, and of course we should put a comment. Saying what this does. Okay. You can, so we've seen an if statement without an else clause. That's what's happening here. We saw an if statement with an else clause. So if you have an if and an else, exactly one of those two clauses will execute. and there's a more advanced form in Python as well, and that's this what's called an elif clause. And I'll illustrate that by way of example, or let's say by solving a problem with it. So suppose I want to solve a formatting problem, and it has to do with someone's age. So let's say if your age is less than 2, then you are an infant. If your age is bigger than or equal to 2, but less than 4, then you're a toddler. And let's say that if you're older than 4 but less than 13, so for age less than 13, you are a kid. And well, let's put one in between there. I don't know, 8, you're a kid. Between 8 and 13, what's the term for those guys? Tweeners. And after that, you are, if your age is bigger than or equal to 13, you're old. Okay. So we want a function that takes an age expressed in years and returns one of these strings. So it either turns this into the string infant, the string toddler, the string kid, the string tweener, or the string old, depending on what the value of age is. So we get this argument called age, and we want to turn it into one of these strings. So, yep. Yes, I did. Yeah. We are recording. We're live, so be careful what you say.
Hi, Mom.
Yeah. Okay, so we know the problem now. We know what we want. We know exactly the inputs and outputs we want. Let's start writing this. So how do we do this? Where do we start? Yep.
You can go, if the age is, you put less than or equal to 2 for your toddler. So you can go, if the age is less than or equal to 2, return toddler.
Well, no. If my age is between 2 and 4, I want to be a toddler.
Oh, so that needs to be
Yeah. So that's an easy one to identify. If your age is less than 2, you can return infant. Okay. Otherwise, and that's denoted by elif. So otherwise, if something else is true, then I should do something else. So what's the next obvious thing now? We've handled the case where the age is less than 2. What's next? Yep. Yeah. So we've already deduced, if we got this far, that the age is not less than 2, so it's bigger than or equal to 2. And so if it's less than 4, then it satisfies all the conditions we need for toddler, right? It's bigger than or equal to 2, and it's less than 4. So then we return toddler. We put another one of these. If that's not true either, then the next step is between 4 and 8. Well, we already know that the age is not less than 4, so it's bigger than or equal to 4. So if it's less than 8, we'll return kid. If it's less than 13, we'll return tweener. And finally, if it's not less than 13, it must be bigger than or equal to 13. We can return old. So let's test that out. Yep.
You said if it gets to a return statement, the program goes to end, right?
Not the program, just the function. So in this case, the function age as string. Yeah.
So is there any need for the else in that if, or can we just leave it as multiple ifs instead of
Yep. We could also drop the else. The same way we did for.
I mean for all the ifs.
Yeah,
Yes, you could drop those, but well, so let's say we're really anal about having only one return statement per function, then we could write this way instead. Say the return value, instead of returning here, toddler. Good. Finally, else. And now we can write this function the way some people really like, with one single return statement in the function occurring on the last line. Yep.
is return val an actual thing, or is that just some name that
It's
you
just
give
a variable name. Yeah. So let's test that. Age is string 23. That's old. Age is string 1.5. That's an infant. Let's take 3. That's a toddler. 5 is a kid. 9 is a tweener. And yeah, and then we can go up to 14. That's old. And what about 13? Old. So the rule is strict here. You have to be strictly less than 13 to be a tweener. Once you're 13, you're a teenager, which is old. Okay. So this is a really common sort of thing that you have a variable, and it's sometimes a number, and you want to classify it this way. So so here's some classifications of ages. But I think on the assignment there's a few questions like this where you want to do something like determine whether a number should be expressed in kilobytes, megabytes, or bytes, or maybe gigabytes. As well, there's one question about converting time into something that you read. So a number that represents a time into something that you read.
What is ELIF again?
So ELIF, you read it as else if. So it's equivalent to this, and I'll show you what it's equivalent to, and as well, while doing that, you'll see why it's nicer to be able to do it this way. It's the same thing as writing else if. So instead of ELIF age less than 4, I can have an else clause, and then that else clause starts with an if statement that says if the age is less than 4. And now if I try and get rid of all of these that way, you see what starts happening. This thing starts to get out of hand. So this is not exactly a lot of cases. There's only 5 here, and you see that this is now starting to run across the page. If there were 15 categories, we'd run out of width in our editor. So ELIF, you just read it as else if. And it always follows. It basically always follows an if statement or another else if statement, and then you close if you want with an optional else. So it's usually if any number of these things, and then you can close with an else if you want. It's a good rule of thumb not to nest if statements too deeply, because if you do, then well, the deeper you do it, the more complicated your code becomes to understand, basically. And here, I mean, there's code that is that complicated, that there's a sequence of decisions that has to be made which is that deep. But if that happens, you should think about redesigning your code in some way and maybe making some of those decisions into their own functions that hide that. Here, it's not really necessary. Well, you see that this is a fairly common construct where you have a bunch of different, slabs that you're interested in, and you use a sequence of these else if statements. Okay. Questions about that? Yeah. Oh, definitely. If it's this kind of function, that really all you're doing is taking a single number and splitting it up, deciding on a few different cases of ranges where that number should be, then else if is definitely the way to go. This nested thing is horrible, right? I mean, it's horrible to look at, and it's also a potential source of errors for indentation or any other number of problems. So this else if form is much simpler. Okay, no questions about that? Good. Okay, so now we need to talk a little bit about Boolean logic. So we've already seen that if I ask questions or if I do comparisons like 4 less than 5, the answer is true. So, and if I say is 4 bigger than 5, the answer is false. So true and false are Boolean values. We often associate them with 1 and 0, respectively. In Python and in many other programming languages, you can interpret integers as Boolean values. In fact, you can interpret almost everything as Boolean value. And the rule of thumb is if it's 0, it's false, and if it's anything else, it's true. So we will generally try to avoid that. So when writing if statements and things, what we usually want as the condition is something that really gives you the value true or false, not some number. It's a little bit strange to write something like if 2 plus 2, although it's perfectly valid. It's not really clear what it means, and it looks like it's potentially an error. So we'll generally try to avoid that, but know that it does happen, and sometimes you'll come across it in code. So Boolean values, Boolean values you can do operate. They have their own set of operations that you can do on them, and the 3 major ones are. So let's say 1 less than 2. So AND is a Boolean operator. It takes 2 Boolean arguments and evaluates to true if both its arguments are true, and it evaluates to false if even one of its arguments is false. So, so here 1 is less than 2. Is that true or false? True. 3 is less than 4. That's true. So true and true. That's true. On the other hand, if I say 3 bigger than 4, then that's false. Because the first condition is still true, but the second one is false, and the AND operator requires both its arguments to be true, otherwise it evaluates to false. Actually, a little bit more precisely in Python, the AND operator requires its first argument to be true, otherwise it evaluates to its second argument. So if you want to see what that means, it requires its first argument to be, well, if its first argument is false, it evaluates to false, otherwise it evaluates to its second argument. So let's take a look at that. If I say 1 less than 2 and 3, the answer is 3. So that's a little bit weird. It makes a lot more sense when you have Boolean arguments on both sides, and then you can't really tell. So try not to write expressions like that. Okay. So another one of these things is OR. So that's OR is another Boolean operator. It takes 2 Boolean arguments, and it will evaluate to true if either of its arguments is true. So if either or both of them is true, then it's happy. So it only needs one of its arguments to be true, or to evaluate to false, it needs both its arguments to be false. So true or true, that's definitely true. True or false, that's also true. But false or false, that's false. So so it really just needs either it needs its first argument or its second argument to be true in order to evaluate to true. And sometimes this gets confusing for people because this is a little bit different than the way we use the word or in English sometimes. So you might say something like, I will go out tonight or I will stay home. And in English, that's usually understood to mean that you're going to do only one of those things. But in Boolean logic, you could do both of those things. So it makes perfect sense in terms of Boolean logic for me to say, I'm in this room or I am behind this desk. So I'm both of those things, and so that statement is perfectly valid. Both of those things are true. It's also okay for me to say I'm in this room or I'm outside of this room. One of those is true. But it's not okay for me to say, well, 2 things that are both false. Like right now I'm outside this room or I am playing the piano. Neither of those is true right now. Okay, so questions about AND and OR? Any other Boolean operations we know of? Yeah. Not. So AND and OR are great, but they're not enough, and we need a little bit more to have a full set of Boolean operations. And what we need, or what we need, something we could add to this to make it complete, is the negation operation or the not operator. So 1 is less than 2, that evaluates to true, but there's this unary Boolean operator called not that takes 1 argument, so it's like a minus, it's like the negation operator, like the minus sign, and it just changes its value from true to false or from false to true. So true goes to false, and not false, that evaluates to true. Okay, so just put the not before a Boolean expression. Okay, so we talked about order of operations before, and we said we had bedmass. Those are the ones you're used to: brackets, exponentiation, division, multiplication, addition, subtraction. We saw that we could add to that comparisons. So that's this less than, greater than, equals, all of those things. So in this picture, in this list of things, where do the Boolean operations go? Where do AND, OR, and NOT go? What's that?
Before everything.
Before everything? Is that true?
Or perhaps after brackets, but
Yeah.
At the very, very end.
Yeah, so it actually goes right at the very, very end. So comparisons, remember, they have the lowest order of precedence because typically you have some mathematical expression with pluses and minuses and all this other stuff is less than, or some comparison operation, some other expression, and you would like to evaluate those two expressions before you compare them. And actually, the Boolean operations want to go even after that. So here, for example, so I don't know what we're going to write for Boolean because we're already using B, so let's just put bool there. So in this example, this is not 1 less than 2, right? That's not the way we evaluate this thing. It's the other way around. We first check if 1 is less than 2, and then we evaluate that. And same thing here, 1 less than 2, and 3 less than 4. We turn these two comparisons into Boolean values, and then we take the end of those two Boolean values. So, so these logical operators, they're at the bottom of the pile here. They're the last things you do. Yep.
What does the C mean in the?
C was comparisons.
Oh, okay, sorry.
Yeah. So you don't typically run across that in the usual description of them, although you should in some sense, because when you do algebra, you have things like A is equal to some expression. A is equal to B plus C, for example. And that's not like saying A equals B and then later plus C. It's really A is on one side, there's B plus C on the other side. First figure out what B plus C is and assign that to A. So, so the comparisons are really at the bottom of the pile. So even though you never learn about them, it's somehow implicit. And then these Boolean operations are even further down than that. Okay, so we'll see some examples of maybe writing some of those. Let's write a simple function that reads input lines using raw input, lines of input until user enters a blank line. So it uses raw input to read lines of input. Yeah, so it'll use raw input to read lines of input until the user enters a line with nothing on it. So they just press enter. All right, so that's a description of the function. How do we start? Yep.
You can check if the length of the input is weighted at 0 and ask for it.
Okay, so we should maybe first thing we should do is read some input. Yeah. So okay. So we read it, and then something like this: if len of s equals 0. Then we can return, let's say, because we know return gets us out of a function. And if len of s is not equal to 0, then what do we do? I don't want to do that. I don't want to introduce recursion just yet. Yeah. Well, we read some more input, right? So we could, and if that's not empty, we can read some more and some more and some more and so on. So there's a function that does that. Yep.
Are there do while loops in Python?
And there's while loops in Python, which we're about to see. So so you see, yeah, you can write this function up to a point, and it'll keep reading lines of input. But eventually you get tired of pasting this same piece of code over and over again. Although we can just check that it does work. And now I'll enter a blank line, and it finishes. So this does work, but it only works up to a point. We can, it's only as many times as we're willing to paste this line of code here, and it's not terribly compact either. So to make our language Turing complete, we can introduce while loops. So a while loop is a little bit like an if statement. It takes a condition, and the way you read it is you say, while this condition is true, do this block of code. So an if statement says, if this condition is true, do this block of code. A while loop says, while it's true, do this block of code. So the thing we want to continue in this case if the length of s is not equal to 0. So this is one of the comparison operators. Bang, exclamation point, equal. That means not equal to. So while the length of s is not equal to 0, or if you don't like not equal to, you can say bigger than 0, because it's certainly not going to be negative anyway. Then we can read another line of input. So it looks like an if statement, except rather than just executing this block once, it will execute it repeatedly until this condition here stops being true. So you better put something in that block that could change this, change the value of the condition. In this case, we did. We read a new string s. As many times as we want until we finally enter a blank line. Okay. So is a while loop clear how that works? Okay. So it's, if you understand an if statement, then there's not much more to a while loop except that, if statement executes a block of code once, and a while loop will execute it potentially forever, or at least until the condition stops being true. Okay. Now these while loops are actually pretty important because they're the first thing we've seen that allows us to execute something for a number of times that we didn't have to specify. So that's called, in theoretical computer science terms, that's called unbounded iteration. So we can write a while loop that actually runs forever, or for some number of times that we don't know in advance and we have no way of specifying. So if we think about our other loops, we have these for loops, but those for loops work on arrays, and we somehow have to define those arrays, and we only know a few ways to do that. Either you type them in by hand, element by element, or you call the range function, but the range function takes arguments, and so that determines how big the array is. Whereas a while loop, you really don't have to specify in advance how long it can run, and it can run forever. That's important, and actually that's what makes the language complete at this point, meaning that anything that we can compute with a computer, we can compute using what we know from Python now. So let's take a little digression to a little mathematical digression. And I want to talk to you about something called Collatz conjecture. Has anybody heard of this? Or the Collatz conjecture? So it's this interesting little idea, and the conjecture. So a conjecture is something that someone believes is true, but they're not able to prove that it's true. It says that if I start with any positive integer n, and I do the following: if n is even, I divide it by 2, and if n is odd, then I multiply it by 3 and then add 1. And then I do that again to the number that I get. So I keep repeating this thing. So the Collatz conjecture says that that will always finish with you finishing, the sequence will always go down to 1. Okay. So it's a little bit surprising because, well, the sequence can go up or down, right? Sometimes it increases by a factor of 3 plus 1. Sometimes it decreases by a factor of 2. But it feels like those increases should be bigger, right? You're multiplying by 3, you're only dividing by 2, so it feels like this thing should be getting away and going off to infinity somehow. But that doesn't appear to happen. So the conjecture is actually eventually you always get down to 1. So very difficult to prove. And the reason it's difficult to prove is, well, the conjecture says that this is true for every positive integer, and there's infinitely many positive integers. So we can't just check them all. But we have a computer, so we can check a lot of them. So let's try and write a function that checks the Collatz conjecture for, let's say, one value of n. So I start with the value n, and the rules of the Collatz conjecture say, well, if n is equal to 1, I'm done. Otherwise, I should apply this rule of either multiplying by 3 and adding 1, or dividing by 2. So this sounds like a loop, right? So sounds like a while loop. What's the condition to keep so if we use a while loop, what's the condition that says we should keep going? We're not done yet. Yep.
Well, it doesn't equal 1.
Yeah. So as long as n is not equal to 1, we should continue. And, well, what does it say we should do then if we're continuing? What are the rules? Okay, if n is even, well, n is even is, we can write that as n mod 2 equals 0. Remember, mod is the remainder after division. So if the remainder after we divide n by 2, if that's equal to 0, then we should, so n, that means n is even, so then we should divide it by 2. So we say n equals n divided by 2. And here I'll use the div operator, that's integer division. Is there any danger that we might make a mistake by using integer division? In this case? Some people are saying yes. Some people no.
Oh, no.
No.
There's nothing to cut off. So.
Yeah, so we've already checked that n is even. So it is divisible by 2. If we divide by 2, there's no remainder, so we might as well use integer division. And otherwise, if it's not even, then it's definitely odd. So we say n is equal to 3 times n plus 1. Okay. And, well, it'll be kind of boring maybe if all we do is, so something interesting here, this while loop, we have no idea whether or not this loop finishes, right? If the Collatz conjecture is true, then this loop will definitely finish because we'll definitely get down to 1. But if the Collatz conjecture is false, and we happen to give it a value of n for which proves that it's false, then this loop will run forever. It'll never get down to 1. So this is something really different than anything we've seen before. So Collatz 50 runs. Not really that interesting, right? Collatz 5000. Oh, put an I in there. That also runs. Not terribly interesting. Maybe we'd like to look at what these numbers are. That might make it a bit more interesting. let's try Collatz 50. 50 is even, so we divide it by 2, but 25 is odd, so we multiply by 3 and add 1 and get 76, which is even, so we divide by 2 to get 38, then 19. Oh, but then back up again. That's even. We divide, back up, down, up, down, up, down, but eventually it gets down to 1. 99, 100, 1,000, some really big number. It's true for that number as well. It's kind of a longish sequence. There's all the numbers that it had to go through to get there, but it did get down to 1. Okay, so that that means we've now written a function that we can use to test the Collatz conjecture for one particular value of n, but the conjecture says that this is true for every value of n. Can we write a function that tests that? Yeah. Yes?
You go for n in range, and then whatever range you want to do, and do that for each number, it'll test it.
Well, I don't want to do for n in range. I want to test it for all the numbers. Not just the ones up to 1 million, or not the ones up to 1 billion, or not 1 trillion. I want to do for all of them. Can I do that?
There's a function for Python's highest integer.
Well, there is no highest integer in Python. They're arbitrarily large. Yeah.
Can you set a while loop that will never end, and then just copy paste in your code that you have into that while loop, and then add +1 to that? If it returns, if that ends up returning 1, then just add a case at the bottom that goes table then n +1 equals n.
Okay. So the idea is that, well, we can start with n equals 1. We can test the conjecture for that. I know that it's true, but that's okay. We want to make sure it's true for all of them. And now we want to loop. Well, it's going to be forever, right?
Yeah.
So we'll write a while loop whose condition is always true. So there's a condition that's always true. 1 is always less than 2. And I'll call Collatz of n. Yep.
Can you just write true instead of
Sure. Whatever you like. However you prefer. So then I'll call Collatz of n. If that finishes, well, that means it was true for that value of n. And now I just say n equals n plus 1. And again, this won't be interesting if we don't print something here. So, and it also won't be interesting if we print this sequence for every value of n we test, because it will just give us a big sea of numbers. So let's just try and do a running counter.
If you leave that bottom one, it'll just do 1 and 2.
What's that?
If you leave the bottom one, it won't, when you call cost, once your while loop is done, it'll print it, and then you'll call your test Collatz again.
Yeah. Well, but that bottom one will just print 1 every time. So if you get to the bottom here, it's because n is now equal to 1. So that won't be interesting. A little bit easier is, or a little bit nicer is if we print %d /r percentage n. Let's try that. And so there we go. This is now printing the numbers as it tests them. So we're up to 200,000 now. 300,000. So, you know, the conjecture on the face of it, the first time you hear it, you think, oh, that can't be true. On the other hand, you can write a program like this that can check it, and already we know that it's true for the first 500,000 integers. In a few seconds, we'll know that it's true for the first 1,000,000 integers. Yep.
Why?
We don't know. if we knew that, we'd be able to prove that it was true. So just seems to be true. A famous mathematician named Collatz. So he said, he has a famous quote that's after being told the Collatz conjecture, he said, "Mathematics isn't yet ready to study these kinds of problems, and yet science is ready to get evidence about them." So let's kill that. Okay, so there's just a little digression, and take that program home and test it on your machine. See how high you can verify the Collatz conjecture for. So what happened? How would we know if it was not true? Well, would the program crash? Yeah. So the loop would get stuck on one number. It would get stuck on the number for which it's not true, right? So either the thing goes down to 1 or it just keeps jumping around forever. So if it gets stuck on one number, do we know that it's not true? It could be that it's just for that particular number, it has a really long way to go. So actually, in some sense, this program is completely useless because it can neither prove it nor disprove it. But certainly if it gets stuck on one number, that would be a good sign that we should take a good look at that number and see if we can focus on that to disprove it. And in most cases, it's actually a fairly short sequence of numbers that takes you back down to 1. So if you run across one that you saw how quickly this was counting, right? Most of the time in this program was actually just spent printing the numbers rather than doing computations. Printing to the screen is much more work than verifying this thing. So you see that. Okay, so now I want to put everything together and maybe learn a lesson at the same time. I want to write a little game. It's going to be a silly game, but that's fine. And so anybody played this game before? I'll guess a number between 1 and 1,000, or more likely the computer is going to guess a number between 1 and 1,000, and then you're going to try and guess it. And you'll get 10 tries, and each time you make a guess that's wrong, the computer will tell you whether you were too high or too low. Anybody played this game before? Yeah. Can you win this game?
Yeah.
Well, let's see. Let's see if you... First of all, can you write this game? Second of all, can you then beat this game after you've written it? Okay, so there's the problem statement. Create this game. How do we start? Yeah. So first thing is the computer better guess this random number and not tell us. So it's important that the computer is able to keep a secret. So we need to make a random number. We don't know how, so we Google it. And as usual, Python followed by whatever it is we're looking for in Google takes us to the answer we want. Python documentation says there's a whole random library, and in that random library there is a rand int, return a random integer n, where n is somewhere between a and b exclusive. It takes these two arguments. That looks like what we want. We want a random int between 1 and 1,000. So x is equal to rand int 1,000. Random. And we want the random, we need the random library for that. Okay. Computer made its guess. It's going to tease us. Okay, and now what? Yep. You have to talk louder, sorry. Yeah, so we should ask the user to maybe make a guess. So G is a good variable name for a guess, and we wrote a function up there called read a number that prompts for a guess and reads it. Okay. Now what? Yep.
We read if else statement saying if it is less than x, tell them it is less than x, if it's greater than x, greater if it is x, then tell them.
Okay, so if g is less than x, then we should do something like, say, print wrong to low. The more exclamation points, the more fun your game is. Else if g is bigger than x, print wrong to high. And else print right. You are a winner. Okay. So far so good. So now what do we do? Copy this 10 times? No. So that's one solution. We now have a piece of code right here that we can copy and paste this 10 times and we've solved the problem. But not the nicest solution. Yep.
Right from when you prompt the user to put in a number,
Yep.
you nest it into a while loop. But before you do that, you define a variable. You call it something like tries.
Yep.
And you say tries is equal to 10 since the user gets 10 tries. And then you nest every other thing inside into a while loop.
Okay.
At the end, as long as the user fails it, you deduct from the variable try. So the while loop condition will be while tries is greater than 0.
Okay. While tries is greater than 0. There's actually, we'll see there's a few ways to do it. We actually probably want a fancier condition on this. There's sort of two things that finish the game, right? You run out of tries, or what else? Or you guess correctly. So I should continue while tries is bigger than 0, or what? So I'll continue while you still have tries, or your guess is wrong. That's g is not equal to x. So then actually, this last statement, this else statement, doesn't make sense here because it'll never happen, right? Because the guess is wrong. We will never be in this while loop if the guess is correct. So let's get rid of that for now. We'll see where we should put it later. Okay, wrong too high, wrong too low. doesn't, yeah. We do need that inside the while loop, but it doesn't have to be at the beginning of the while loop. In fact, it should probably be just at the end. So a couple of things we should do. Maybe we could, each time you make a guess, you've used up one of your tries. And just to make things stressful, we can keep telling the user how many tries they have left. And finally, okay, so we read the number, we got into this loop, we told them that they were in this loop, so it was wrong. We told them they were too high or too low. Now we give them another try. And actually, see if this works. Then we read a number again, and the loop starts over. Yep.
Wouldn't for your conditional for your while statement, wouldn't it need to be end? Otherwise, even if you guess correctly, if you still have tries left, it's going to continue anyways, because one of those conditions would still be true.
Yeah. So it is an end. So we continue while you still have tries left and you haven't guessed correctly. That's right. Otherwise, it's going to play through till you guess correctly and you run out of tries. Okay. And then maybe at the end of this thing, we should either, so once the while loop is over, it could be over for one of two reasons. Either you ran out of tries or you guessed correctly. We should either congratulate the player or not. So we'll congratulate them if they guessed correctly, if their last guess was correct. And otherwise, okay. So there's our whole beautiful game in its entirety. Okay. Is it going to work? It's a lot of code. There's bound to be a mistake in there. Let's see. At least it didn't give us an error when we loaded it. There's an error. Randint. It's imported up there. Let's. Yeah. So randint is randint, all one word. Try again. So by the way, just as a matter of you guys learning, that is a lot of code to write in one sitting without testing along the way. So if you try and do this, there's a good chance you'll run into lots and lots of problems. I'm doing it so that we can finish class on time today, but generally you would build this up a little more slowly than that, something this complicated. Okay, so this thing is teasing us. What do we do? Too low. 750. Too high. 625. Too low. 675. I'm going to go with 675. Too high. 650 seems to be a consensus. That's a good choice. 35, 45, 640, 630, 635. Too low. 640. You guys are not doing that well. 645. Too high. Too low. So you did something wrong because there was a chance that you may not have gotten it here. So you go read up on binary search. More likely, practice adding two numbers together and dividing them by 2. That's the real thing. So some of these guesses were suboptimal, which is why at the end we almost didn't win. We could have lost there. Yeah. Control C usually. Yeah. You got into an infinite loop. Yeah. So while loops, they lead to infinite loops. It's very easy to make infinite loops. In fact, we wrote one on purpose here. It's also easy to make them by accident. So last little cleanup. Anything we could clean up in this function? I see one little thing we could. Yeah.
Clean up the while. Set tries to 0. Oh, never mind.
Push down. Remove the read a number and what they call it. After the tries, you subtract tries, and then you carry down read a number that's outside the while loop and put it right on top.
Yeah. So we could clean this up a little bit. It would look like, well, it's actually a little bit, it's not clear that that would be a cleanup because then we'd have to handle the case where it's equal. Inside of here.
Inside.
Yeah, and then return. So there's that. So we could have only one place where we read a number and then move this up there. Yeah. Any other thing that we can just delete?
Exclamation marks.
Yeah, we could delete a lot of exclamation marks. That might make it better. Yeah, so there's one else in here that I see that's elif that's redundant. So at this point, we're inside the while loop. So g is not equal to x. We're at this line because g is not less than x. So if it's not equal and it's not less than, it must be bigger than. So this condition is always going to be true. And sometimes when you do this, it's sometimes a handy place to put a comment because it tells somebody who's reading your code that I've deduced that g is bigger than x, and I'm telling you at this point that this is the case. That's why I don't need to check it here.
You just have to put the else. Oh, well, yeah.
You do have to put the else, otherwise both of those things could execute. Yeah. Okay, so let's leave it at there for today.
And there's definitely no such thing as a do while loop.
No.